In this lecture, I'm going to discuss the Jordan-Holder theorem. Recall that a Jordan-Holder series for an R module M is a composition series that is strict and has no strict refinement other than itself. So a Jordan-Holder series looks something like M0 contains M1 contains M2. So each module, submodule properly contains the next one. The last one is 0. And there is no way to cannot insert new terms in between. Okay, and more important, equivalently, we could say that Mi mod Mi plus 1 is simple for I equals 0 to n minus 1. Now we've seen some conditions, namely the ascending chain condition and the descending chain condition, which ensure the existence of a Jordan-Holder series. But let's not worry about that right now. I'll state the Jordan-Holder theorem in a more general form, and it turns out to be a direct consequence of Schreier's theorem. So let's state the theorem. A Jordan-Holder, I think the simplest statement would be any two Jordan-Holder series for an R module M are equivalent. Okay, so let's just decode what this is. Firstly, I'm not claiming that an R module has a Jordan-Holder series. I'm just saying that if it has two Jordan-Holder series, they must be equivalent. So what this means, firstly, recall what this means. This means that if you have Mi I equals 0 to n, j equals 0, let's say I equals 0 to m and j equals 0 to n, are equivalent if 1 m is equal to n, and 2 there exists sigma from the set 0 to m minus 1 to 0 to n minus 1, a bijection, which kind of implies that m is equal to n, such that mi modulo mi plus 1 is isomorphic to n sigma I modulo n sigma I plus 1. Okay, and this will follow directly from Schreier's theorem. So proof: suppose mi I equals 0 to m and j equals 0 to n are Jordan-Holder series for m. Okay, so then Schreier's theorem says that, so let's call this sigma 1 and let's call this sigma 2. There exist refinements sigma 1 prime and sigma 2 prime of sigma 1 and sigma 2 respectively that are equivalent. But now sigma 1 and sigma 2 are already Jordan-Holder series. They cannot be refined by strict series. So this sigma 1 prime and sigma 2 prime would just be refinements of sigma 1 and sigma 2, where you are adding more terms which are equal to the existing terms in the series. So what we are saying is that, if you have sigma 1 is something like this, M0, M1, M2, Mn equals 0, then you will be adding terms in between which are either equal to, so you may be adding terms like this, M01, M02, or many more terms or in between. These new terms will be either equal to M0 or to M1. So there are no new terms that appear in sigma 1 prime and sigma 2 prime. And so if they cannot be, so once you take, if we remove the repetitions in sigma 1 prime, it becomes sigma, and if we remove the repetitions in sigma 2 prime, it becomes sigma. But these repetitions are precisely those terms in the series where the quotients are zeros. Right? And because sigma 1 prime and sigma 2 prime are equivalent, they have the same number of zero quotients. So after removing repetitions, which correspond to zero quotients, sigma 1 prime and sigma 2 prime have the same length. So since they have the same number of, sigma 1 prime and sigma 2 prime have the same length, so sigma 1 and sigma 2 have the same length. So you get sigma 1 and sigma 2 which have the same length because sigma 1 prime and sigma 2 prime have the same number of zero quotients. And the remaining quotients, of course, they permute each other, and so if the remaining non-zero quotients still permute each other. Right, so we have a bijection between the zero quotients. After we remove them, we will still have a bijection between the non-zero quotients. And so these two Jordan-Holder series, sigma 1 and sigma 2, have to be equivalent. So we haven't assumed here that M has satisfies the ascending chain condition or the descending chain condition. We just assume that M has Jordan-Holder series. We haven't really assumed that M satisfies the ascending chain condition or the descending chain condition. But just with the assumption that M admits at least one Jordan-Holder series, we can do a lot. So here's a corollary, and this is not a corollary of the Jordan-Holder theorem as stated per se, it's a corollary of Schreier's theorem. Which says that if M has a Jordan-Holder series of length L, N, so let's say Mi, I goes from 0 to N. So that means length, I call that length N. Length N. Then M cannot have a composition series, a strict composition series of length more than N. So every composition series of M will have length less than or equal to N. And the proof is this. So suppose Nj, J goes from 0 to K, is a composition series. Then Nj and Mi, so let's call this so Mj, Mi, I equals 0 to N, and Nj, J goes from 0 to K, admit refinements sigma 1 prime and sigma 2 prime respectively. So sigma 1 prime is a refinement of this Jordan-Holder series Mi, and sigma 2 prime is a refinement of this composition series Nj that are equivalent. Since they are equivalent, they have the same number of non-zero quotients. Moreover, the number of non-zero quotients of a refinement would be at least as large as the number of non-zero quotients of a composition series. So now what we have is N is the length of the composition series Mi, so it's the number of non-zero quotients of sigma 1 prime, and that's equal to the number of non-zero quotients of sigma 2 prime, but that has to be greater than or equal to K because a sigma 2 prime is a refinement of Nj, and so K has to be less than or equal to N. So you cannot have any composition series of length greater, a strict composition series of length greater than the length of a composition series, of a Jordan-Holder series. Corollary: if M has a Jordan-Holder series, then it satisfies the ACC and the DCC. Because if you have an increasing chain, it has to stabilize at some point, because you cannot have a strict increasing chain of length more than the length of this Jordan-Holder series, and the same applies for decreasing chains. Okay, and also the Jordan-Holder theorem gives us a set of invariants for a module. So here's how we compute this. So let M be an R module with Jordan-Holder series M0 contains M1 contains Mn equals 0. So this is going to be strict and these quotients are going to be simple. The simple modules, so we'll call this mu of M, define mu of M to be the multiset M0 mod M1, M1 mod M2, Mn minus 1 mod Mn. So we remember the multiplicities with which the different quotients arise. So this is the multiset of quotients. This is independent of the Jordan-Holder series. This is what equivalence means. For example, we had looked inside Z mod 12Z. So let's call this M. This is a Z module, and this had submodules. For example, we have a Jordan-Holder series which is M, contains 2M, contains 4M, contains 0, and the quotients here are Z mod 2, Z mod 2 and Z mod 3. So mu of M is Z mod 2Z, Z mod 2Z, Z mod 3Z. A multiset. Okay, and this doesn't depend on the composition series. And if you have two isomorphic modules, then these multisets are equal. The size of this multiset is called the length of the module. So definition, length of M is defined to be the length of any Jordan-Holder series of M. Just to be doubly clear, if I goes from 0 to n is a Jordan-Holder series, then we'll say that length of M is equal to n. So what we have in this example is that the length of Z mod 12Z is equal to 3.